Hi, and welcome to this video on the vertex of a parabola. The first curve most of us learn to graph is a parabola. Before that, we all learned to plot points on a number line and on a coordinate plane. Then we graphed the lines of linear equations, which only required 2 points and a ruler to keep things straight. Once we mastered that, it was time for the parabola. A parabola is the graph of a second-degree function. That means the variable, usually x, has an exponent of 2. The linear equations we learned to graph earlier are first degree, so that x has an exponent of 1, though it's usually an invisible exponent because we don't usually write that little 1. A linear equation is most often found in slope-intercept form, like this. We can even write it with the exponent so we can see the first degreeness of the equation. It's the same thing, and though it's a little bit confusing to have an invisible exponent, we should be glad we don't have to write that little 1 every time we write a variable that is first degree. Here's an example of a second-degree function. Notice that our y turned into an f of x. This is called function notation, and it looks a lot more complicated than it really is. It's just a way for us to keep track of our functions when we have more than one, such as when we have a system of equations. We can use f of x instead of y with linear equations too, but most of us didn't learn function notation until after we learned linear equations, so we're more accustomed to the y. Okay, let's get back to the second-degree functions. One thing we definitely need to know is that they're often called quadratic functions. So whenever we hear quadratic function, we need to remember this means second degree, which means the highest exponent on the variable is a 2. Now compare this to the standard form of a quadratic function, which looks like this. F of x equals ax squared plus bx plus c. In this form, a, b, and c are constants, which means that they are numbers. In our example, a equals 1, b equals 2, and c equals negative 3. Notice that the coefficient of our x squared term is invisible because it's a 1. This is very common with quadratic functions, so we need to remember that whenever we can't see our a, it's because it's another one of those invisible ones. Being able to identify our a, b, and c are very important for finding the most important points on the parabola so we can graph it efficiently. It is true that we could graph our quadratic by finding points on the curve by plugging in values for x and getting our y values. The problem is that it's not always easy to find the top or bottom that way. Here's a graph of our sample function with the most important points highlighted. The x-intercepts are sometimes called roots and can be found by factoring, completing the square and the quadratic formula. The y-intercept is easily found when a quadratic function is in standard form. It's the c. In our example, c equals negative 3, and on our graph we can see that our y-intercept takes place at the point 0, negative 3. The last point is the vertex, which might just be the most important point on any parabola. The vertex is either the top or bottom of a parabola depending on which way it's facing. For our example, the vertex is the bottom of the parabola. We can easily find its location on the graph, but how do we find it when we only have the function and not the graph? We start by noticing something important about parabolas in general. They are symmetrical. We can see the axis of symmetry shown as a red dashed line and can imagine folding our graph on this line and holding up our paper to the light so we can see the two halves of the parabola overlapping each other. Perfect symmetry. The axis of symmetry can be found using our a, b, and c. Well, we don't really need c, but since we already used it to find the y-intercept, it won't feel left out. Here's the formula for finding the axis of symmetry. X is equal to negative b over 2a. Remember that when we have an equation written as x equals a number, it is an equation of a vertical line. That's what we're trying to find here. Let's take a look at our sample function again so we can find a, b, and c. F of x equals x squared plus 2x minus 3. Remembering that a, b, and c are shown, or not shown if invisible, from left to right, we can find that a equals 1, b equals 2, and c equals negative 3. Now we can plug a and b into our formula for axis of symmetry. X is equal to negative b over 2a, which is our formula for the axis of symmetry. If we substitute our values of a and b using parentheses, we'll get that x is equal to negative 2 over 2 times 1. Now we evaluate the numerator and denominator. If we multiply the denominator, we'll get 2, so x is equal to negative 2 over 2. Finally, we simplify by dividing, so x is equal to negative 1. Now we see that our axis of symmetry is the line x equals negative 1, just like we see on our graph. Notice that the vertex sits on the axis of symmetry. That means the x value of the vertex is the same as the x value of any other point on the axis of symmetry. In this case, it means it's negative 1. Now we just need to find the y value of the vertex. We do that by substituting our x value into our function. So our function is f of x equals x squared plus 2x minus 3. And we plug in a -1 anywhere we see an x. So we'll get f of -1 is equal to -1 squared plus 2 times -1 minus 3. Then if we square -1, we get 1, and if we multiply 2 times -1, we get -2. So we have f of -1 is equal to 1 plus -2 minus 3. When we add and subtract these numbers, we are left with -4. So f of -1 is equal to -4. And that's the y value of our vertex. Now we know that our vertex is at the point -1, -4, and that's exactly where it is shown on our graph. So far we've been using the standard form of our quadratic function, but there's another form called vertex form. We can convert from standard form to vertex form by completing the square, which is a whole big process that we don't actually need for this problem since we already found the vertex. The coordinates are all that we need to write our function in vertex form. This is what vertex form looks like. F of x is equal to a times x minus h squared plus k. The a is the same a from standard form, so it just carries over. Remember that the a is invisible for this function because its value is 1. The two new letters, h and k, are simply the x and y values of the vertex. Since our vertex for this problem is the point -1, -4, that means h equals -1 and k equals -4. Now we can substitute the values for a, h, and k into our general vertex form equation. Notice that we have a subtracting and negative situation happening inside the parentheses. When this happens, the two negatives cancel each other out and become a plus sign. Just like with our standard form, we don't have to write the a if it's a 1, though it's certainly not wrong if we do write it. Just note that it won't usually appear, so the equation will probably look like this. So far, we've found the vertex from a quadratic and standard form. How is the process different when our function is presented in vertex form? Let's try a new problem. Here's another quadratic function. F of x is equal to x minus 3 squared minus 7. Our goal is to find the vertex. Since our function is in vertex form, we just need to identify h and k. The key is to be careful with the signs. Here's our general vertex form equation again. Before we extract our h and k, we need to make sure our signs are correct. There should be a subtraction sign inside our parentheses and a plus sign after it. In the function, the subtraction sign is right, but the plus sign isn't. But that's okay, we can simply rewrite the subtraction as adding a negative. Now that we have our signs correct, we can see that h equals 3 and k equals -7. So our vertex, hk, is equal to 3, -7. In this type of problem, we don't need to find our axis of symmetry before finding the vertex. If we want to know the equation for axis of symmetry, we can find it from the vertex since the h gives us the value for our vertical line equation. X equals h, so x equals 3 for this function. So how is all of this useful? A lot of real-world events can be modeled with quadratic functions. Gravity problems are the most common. Let's try one. A football player punts a football, and the height of the football in feet is modeled by the function f of x equals -16 times x minus 3 squared plus 53, where x is the time in seconds. How long does it take for the football to reach its maximum height? And what is the maximum height of the football? The function is written in vertex form. The a for the function is -16, but we don't need a to solve this problem. All we need to know to answer the two questions is the coordinates of the vertex. Let's check our signs. Remember, when our equation is in vertex form, we want to subtract our h value and add our k value. When looking at our equation for our football, we see that our signs are correct as written. So now we can extract our h and k. We see that h is equal to 3 and k is equal to 53. So the coordinates of the vertex are 3, 53. But how does that answer the two questions? The problem states that x is time in seconds. So the x value of our vertex is the time it took for the football to reach its maximum height. In this case, it took 3 seconds. The function models the height of the football, so the y value of the vertex is the maximum height, 53 feet. This is what the graph of the function looks like. The football starts at 0 seconds and 0 feet and then reaches its maximum height of 53 feet after 3 seconds and finally comes back down to the ground after a total of 6 seconds. We know that because our parabola is symmetrical. So if it took 3 seconds to go up, it took 3 seconds to come down as well. That's it for the vertex of a parabola. Thanks for watching and happy studying.